Hey everybody, welcome to ACT practice day 5. We're getting into a little bit of geometry review. I'm going back old school with a 20-year-old paint program and me writing with a mouse. So if the writing doesn't look very good, you can just blame the fact that I'm definitely just making this up as I go along, but I think it'll help. We're going to go through the front side of your paper. That's going to be 7 problems together. Then you will do the rest of them on your own. So let's get started and knock this out as quickly as we can with a little bit of a warm-up with isosceles triangles. We've got an isosceles triangle, and I know that because we have lengths of 10 on each of these sides. So when it comes to the angles, we have a vertex angle and then 2 base angles. You can always tell where the base angles are because the congruent sides point to them. So if you have 2 sides that match up and then go to the opposite angle from those sides, you end up getting the ones that match. As soon as you've made it to that point, you have 2 55s. So you're just going to knock out 55 plus 55, which is 110. And then we know that triangles have to add up to 180. So we now just have to figure out what you'd have to add up to 110 to make it total 180. In this case, you would subtract 110 from both sides, and you would get 70 degrees. Okay. Nice little warm-up question, not a lot to that one. Okay, so now we're going to get into some more angle relationships, and we are dealing with a pentagon. One interior angle measures 40 degrees. What is the total measure of all 4 of the other ones? So in this case, the best way to remember this, if you don't know where to go, is to begin with what we do know. In the last problem, we just talked about how triangles have angles that add up to 180 degrees. Okay, so if you have a triangle, it adds up to 180. Then let's say you have a square, or for that matter, any quadrilateral whatsoever. Well, you have 4 90-degree angles in this particular example, so I'm guessing that would add up to 360. It turns out any quadrilateral is going to have interior angles that add up to 360. So if you continue that pattern, something with 3 sides adds up to 180, something with 4 sides adds up to 360. It's not a coincidence that the pentagon adds up to 540 degrees. So all 5 put together have to add up to 540. We have used 40 degrees of it, which tells us we have 500 degrees left. Okay, that is a pattern. It holds true every time. You may have had a teacher at one point in your life that did the n-2 times 180 thing. That is a formula. That is the actual formula for the sum of the interior angles. But let's say it's test day and you forget that because you're freaking out. You can just use the pattern. So triangles, 180. Quadrilaterals, 360. And then it just keeps going up by 180 degrees for each side that you have. So hopefully that gives you a head start on what to do if you ever see one of these in the future. Okay. All right, now, I actually debated this one. When I was going through making my questions, I had a little debate, like, am I going to include this? And I decided I would, and I decided I would put it in the lines, angles, relationships lesson, because the key to getting this question right is understanding the angles. Okay, so one diagonal is 12 inches long. Okay, so I'm going to make that, and I'm going to call that 12. Okay? And then the other diagonal is 32. I'm going to make this the longer one, and I'm going to make that 32. The key to understanding this problem is realizing what we've just created. We've just created 4 right triangles. Whenever you draw diagonals in a rhombus, they are automatically perpendicular. And even if you didn't know that rule, you can take a good look and kind of have an idea of what's going on. Now, resist the temptation when you're doing a squared plus b squared equals c squared. Now we want to figure out what this is, right? We want to know what one side of the rhombus is. And it's really tempting to do 12 squared plus 32 squared equals c squared. But you need to realize that the entire diagonal is 32, and this entire diagonal is 12. So if we're going to make a right triangle out of it, we're going to have to cut that in half. So what we actually need to do is 6 squared plus 16 squared to knock it out. Now at this point, you would be crossing your fingers. You'd be hoping that you had Desmos available to you, because these numbers are going to get pretty big. But that's okay, because you will have it available. And even if you didn't, you could use a little $5 calculator for this one. It wouldn't be a big deal. And you have 292 right here. Now I'm going to save you the trouble. It's going to be a little more than 17. If you didn't have a calculator, you could just start multiplying it out, working it through. Turns out the square root of 289 is 17. So that's how I kind of knew that the answer was going to be a little bit more than 17. But if you didn't know that, Desmos, whatever you feel like using is all good. Okay, let's keep on going. Speaking of perpendicular angles, we interrupt this geometry to bring you an algebra special report. What is the slope of a line perpendicular to the line determined by the equation 7x plus 4y equals 11? Now, I'm not going to put Desmos up on my screen right now, but I am going to tell you right now, if you were to graph this line, and this surprises a lot of kids, even my most advanced students don't realize this right off the bat, but this line actually has a negative slope. If you were to graph this line, it would actually have a negative slope. And the reason is, if you were to try and get y by itself, back in the old days, you had to get y by itself before you graphed. Nowadays, Desmos will do it for you. But if you moved things around to get y by itself, you would have to move the 7x to the other side of the equation, which would then make it negative, and then you would have to divide by 4. So it actually turns out the slope of this line is negative. Now, if you are in Desmos right now, if you're trying to work through this problem and you're on Desmos, I would just count squares. Eventually, if you picked some squares, you would find out that it would be going down by 7 and then over by 4. So even if you didn't know the algebra, you would be able to count squares and realize that the slope of this line is negative 7 over 4. Now, you need to resist the temptation to choose letter G. It didn't ask you for the slope of the line. It asked you for the slope of a new line perpendicular to the old line. So now we need to think about what it would look like if we made a new perpendicular line. What would the new slope be? And you can see just by my little sketch here, it's actually going to have a positive slope. The trick to perpendicular slopes is you have to flip it and change the sign. The official phrase that your teachers usually try and teach you is opposite reciprocals. If you do opposite reciprocals, you will get perpendicular slopes. That means what you have to do is flip the fraction and change the sign. So if you flip 7 over 4, you get 4 over 7. And instead of making it negative, you're going to make it positive. Okay? So if your original slope is negative and you want to do something perpendicular, you need to make it positive. So the answer to this question is actually letter K, which you could probably make a good guess if you just looked at this and thought to yourself, well, it's up some, over more, it's less than 1. The only answer left that was less than 1 was K anyway. So I think you could probably make a good guess. Okay. All right. We have just a little bit more that we need to do here. This is going to be a flashback into your old-time parallel lessons. And this is going to be where your teacher taught you if two lines are cut by a transversal, and then you had to learn all the names. Like this right here would be corresponding because they're both on the upper left-hand corner. Okay, so those would be corresponding angles. Then you would have alternate interior, as in they're both inside, but they are alternating sides. So you've got one on the left, one on the right. So you learn all of these relationships. In this particular case, the relationship that they want you to think about is the alternate interior angles. We learned back in the day that alternate interior angles are congruent. So if we go back to our little diagram, if I told you this was 110 degrees, then this right here would also be 110 degrees. That's just the rule, which means if I'm looking at letter Y and I went to the alternate interior angle, again, we have to go with the same transversal here. So you can ignore 1 and 5. They're not even on the same transversal. They're not even on the same line that's cutting through the parallel lines. So you can ignore that, ignore that. We want to go alternate interior, which would put us at J. Okay. All right, now, the ACT is going to use a lot of trapezoids. So this next question is a great segue because the ACT is going to use a lot of trapezoids. And the reason they're going to use a lot of trapezoids is because trapezoids are a great example of what we just talked about. Two lines cut by a transversal. And we could even do the alternate interior again. So if you have a 125 degree angle right here, and you went up to the alternate interior angle here, that would also be 125. Now, that wasn't what they asked for, but it is going to be helpful to us because now we have a triangle, and we know that all triangles have to add up to 180. So if we have 25 and 125, now we are at 150, which means we only have 30 more degrees to spend on that missing angle right there. So the answer is 30 degrees. Okay? Whew. All right, we got to the last question, and the last question is asking what is not true in this diagram, and we have so much going on. This is ridiculous. So let's see what we can come up with. Okay? We have isosceles triangles, circles, diameters, radii, parallel lines. Oh man, everything is going on here. Let's take a quick look. First of all, we haven't talked about vertical angles yet, but it's good to talk about vertical angles. Anytime you have two lines that cross each other, you can go opposite and know that they're going to match. So it turns out this angle has to also be 40 degrees. Okay. Next, I look at this and I look at these diameters. Okay, so we have diameters. So we have a diameter here, and we have a diameter here. They cut your circle in half, which means we're going to have 180 degrees total on each half. Okay, so if I were to go over here, I have 40 and 40. I'm looking over here just at this area right there, and I know that I have 40 and 40. That leaves me with 100 left. So that will kind of steer us in the right direction. Okay, so now let's start looking at these options and see what we can actually come up with. Option F, BAC measures 70 degrees. All right, well, let's take a look. BAC measures 70 degrees. So that would have to be, BAC would have to be 70. Take a look. We have 70 degrees. Well, if we treat this as a radius and we treat this as a radius, it reminds us that ABC is an isosceles triangle. So that means we would have to have a couple of 70s to make it work. 70 plus 70 is 140, plus 40 is 180. That statement is true, which means F is not the correct answer because we want to find the option that is not true. All right, AB is parallel to EF. Okay, so we're going to take a look right here. We have vertical angles. Okay, we have isosceles triangles. We have vertical angles. They are running perfectly side by side. They're going to have the exact same angle measures. We have another 70 and another 70. These are parallel lines, and I know that because of what we talked about twice already. Take a look at these angles. If we have two angles that match, that means they are alternate interior angles, which means these are parallel. So G is not the answer. All right, AB and BD are congruent. Well, if we've got 40 and 70, 40 and 70, we've got these triangles are completely matching. We could get into our angle side relationships from back in the day if we wanted to, but I'm just going to move on. I'm feeling pretty good about this. Okay. BCE, we're almost done here. We got BCE. Ooh, that's 40 plus 100. BCE is 140 degrees. Okay, let's keep that in mind. DCF, okay, DCF, that's 100 plus 40, so that's 140 degrees as well. Yep, that one checked out. The only statement here that is not true is that CF is congruent to EF. And that actually makes sense because although it is an isosceles triangle, the two matching sides are CF and CE. EF is not the same, okay? So I suppose maybe if we would have worked our way backwards the other way, we would have figured that out sooner. But that is the answer. It is isosceles, but it doesn't match them. All right, I hope that helps you on the front side of your paper. Take a look at the back, get them done before you leave, and I will talk to you later.